Hey everyone, thanks for joining today. We're taking a look at this very interesting paper that actually figured out how to have a very good approximation or nearly solve the Schrödinger equation using deep neural networks. And I think it's a really interesting paper just because it really kind of focuses on not only, cutting edge deep neural networks but also really understanding, from given physics principles, how to actually constrain these networks and how to actually train them. So it actually, I think did a really good combination of both, of not only using, the newest methods, but also taking from what we have already known. And so briefly, just going into what the main problem is, the idea is if we can understand this sort of wave function, which is just describing an energy, like a quantum state, a given molecule or something like that. If we can know this wave function, we actually kind of know the properties of it. And so there's a lot of different ways that we've been thinking about how to solve it. One of the couple ways is using like a quantum Monte Carlo simulation, which involves repeated simulations from random sampling of different structures. This actually tends to work out pretty well when you have pretty small molecules, but once you actually get larger molecules, it tends to really take a long time because you essentially have to wait. You have to essentially do a bunch of experiments. That takes a lot of time. And a sort of a similar approach, you can see that this is sort of the same equation we had earlier, but it kind of breaks this up using density functional theory, essentially just a summation of potential energies and interactions between different molecules. And so it's essentially just this sort of weighted, you sum everything together and use that to actually understand your sort of system, all the energetic forces and stuff like that. It tends to be fast, especially for larger molecules, but it's not as fine-grained and accurate. So the idea, this is also based on physics principles, and so it's interesting to think about, and there's been kind of this advance in neural networks, the use of neural networks for a large variety of different tasks, and they've showed a lot of success in a lot of different things, and they seem to be very efficient, especially for this task. In order to do these sort of approaches, you need a large amount of variables, usually to quantify your system. And essentially, the number of determinants is roughly a measure of your complexity. And we see that including neural networks tends to have a lower number of determinants. And this paper had actually a very, very small number of determinants. They're just saying, with relatively simple ease, they could actually figure out how to actually model this Schrödinger equations, model the system for a variety of different molecules. And they end up doing pretty well. And so they used for their main inspiration, or one of their main inspirations, this SchNet, which is stands for Continuous Filter Convolutional Neural Network for Modeling Quantum Interactions. And so I do have a video that goes over convolutions, and you can actually go ahead and check that out in the description below. More detail, but this is just sort of a baseline depiction of a convolution. If we had just had a one-dimensional convolution, we had some sequence, so one dimension just on text. Basically, the first layer we would have it's basically like a sliding window approach. We would examine GAT, and then we have CGA, and then we have TCG. That would be the first layer, and it would have some average of that input. And then for the next layer of our neural network, we would aggregate those two together, or those three. So we have another size of 3 or whatever size we wanted to actually learn the next size. We keep on going up, and so we can get to essentially looking at larger areas of the input as we go on. And so this kind of makes sense for text, but they actually figured out how to do this. SchNet actually figured out how to do the same sort of convolution. This is where this sort of continuous filter convolutional neural network, it's a very complex name, comes from this quantum interactions, is it actually kind of models not going over text, but you're actually have that sliding window over nearby molecules or other molecules or atoms really in position. And so basically, and when, like we were saying, this is just another depiction of a convolution. But this idea is that when you actually do this sort of convolution, the act of doing convolution itself actually constrains very interesting sort of dimensionality reduction spaces. So this sort of transformation, that as you go from 4 dimensions to 8 dimensions, you can actually exploit this in a way to actually model your interactions. So this is sort of the term from the SchNet. The big picture here is that you have these terms modeling each of your intermolecular interactions here, and this learnable weight W. So basically, from the interactions that is happening in this network, we can actually learn this sort of representation to actually understand the network itself. And so I think that this is I'm not going to go too much into detail, but I do think it's kind of interesting to bring up. It is very similar to a lot of other convolutional neural networks. If you have some experience, you might be able to go through this and just see, we have residual blocks here. They even said that they took some inspiration from ResNet. And so I think that right now it's kind of clear that this at least this SchNet was a very very interesting. It was did take into account physics principles, but also did have a lot of just hard deep learning, or just very interesting inspirations from deep learning. But they actually, so this is the sort of differences from the SchNet that this paper that's actually solved the Schrödinger equation, or had a pretty good approximation, that they called PauliNet. And so Pauli is a reference to the Pauli exclusion principle, or the guy who named the Pauli exclusion principle. But basically, each electron has a given spin, and they're not really actually spinning, but they're kind of like polarities, and they can't occupy the same spin if they're right next to each other. And so the idea is that you were actually modeling these sort of physics principles into there. We're modeling things like opposite spin interactions, same spin electrons, and the nuclei individually, using this SDH sort of framework to actually identify and sort of enumerating all of these possibilities between the opposite spins and the same spin. That's where the Pauli comes from, because we're extending this SDH net into actually including these spins. And so each of these has basically, like, the idea is that when you add this sort of learnable function onto your network, and so we can just skip ahead a little bit here. So this is the main sort of network that they're applying here, and we have our inputs, which are the same spin interactions, the different spin interactions, and the nuclei. And given those three, we can sort of learn a network. And so we learn this network from this. We can learn the weights of this Backflow and Jastrow function, which we're going to go a little bit more in a second. And basically what this is we're saying that from this given input, we can sort of constrain and have these different layers of ability to learn, like every arrow of this, or really every orange is sort of a neural network trainable function, orange with this rounded. So we're actually learning these equivalent interaction blocks, this Backflow and this Jastrow, while we actually have fixed functions like this Hartree func, which is like an approximation to this wave function that has been previously solved, and then given other sort of interactions is this cusp that are dealing with these spins and keeping those back. But the main sort of idea is that, given just from our inputs here, we're able to actually get pretty good approximations while constraining our neural network. And the act of combining both the act that we're having this sort of learnable structure where we can learn these weights and how we can actually learn how to calculate these Backflow and Jastrow coefficients, as opposed to numerically solving them, but we're actually learning these different weights, combined with the fact that we're using these sound physics principles, actually lets us get very good approximations, and sort of how this one works. Or that's kind of really why the strength of this is really there. And so I guess I'll just kind of keep repeating that, but that's essentially the main point. And so what they did, it is important to understand that, like in the SchNet, they just kind of looked at different electrons, or they represent, in the PauliNet, they represent electrons, not the given atoms. And basically the SchNet was identifying this particle vector that you would identify here, to actually identify. So based on the inputs, you want to identify this particle vector here that will let you actually understand sort of the system that you have. And they're modifying that. So this is the sort of PauliNet inclusion. So we see, like, at the bottom, we have the interaction with the neighboring terms, which include the positive spin, same spin, or the same spin, opposite spin, and the nucleus interactions. But we basically have the same sort of convolutional approach here, where we take this sort of distance from the neighboring bodies, and we learn these weights. So H, Y, and G are all these learnable network weights, and now we can basically say, well, subject to constraint what we know about these physics principles, how can we actually train these networks to actually identify what we want to? And so this is where we're starting by. So one of the main drawbacks of this approach is actually kind of here. So for each individual system, you have to actually identify and train separately for each energy. So you have to kind of train this network for each molecule that you're looking at. But basically you start with identifying this upper bound of energy. Basically you say, given this constraint, we know that this is the maximum possible energy. And so this is sort of the baseline, the ground state. I think they call it the trial wave function. But basically, starting from this energetic favoritism, we can actually, and using the SDH models, we can actually identify, and knowing this Backflow, I guess we'll go a little bit more in Backflow now. But basically, these are sort of kind of like determined equations that are good approximations for this wave function. But the difference is what they say here pretty much is modeling this wave function via the Jastrow and Backflow functions is common in the quantitative Monte Carlo, but these functions are actually learned with these deep neural networks. And you can do things like actually, so this is kind of again where they're talking about the importance of why it's called the PauliNet, is because they're able to actually identify the spins and constrain these networks that they're learning here, the Jastrow and the Backflow, constrain to whatever effects that they're actually interested in constraining to. And so I guess now we're going to talk about just a little bit about training. I thought this was kind of interesting. So basically, in order to train, they actually generate random data samples. They basically generate samples by sampling electron positions and then training and sampling electrons, and they do it in a way that they never like train on the same thing twice. And so they basically are, and they're generating these using a Monte Carlo method. So they're actually still using the Monte Carlo in addition to the neural network. But then I think this is interesting. So when you're doing this neural network, you need a derivable loss function to actually backpropagate and do your stochastic gradient descent, which is what they did here. But this has the interesting property of this wave function actually being, or the loss that we're interested in here, actually the first derivative of the loss, or it's easier to calculate the derivative loss than the loss. And that's all. We don't actually need the loss to train the neural network. We just need the derivative. So it's kind of interesting that the math also does kind of work out to be a little bit convenient. So I'm not going to go too much into detail with the results. I think the results are pretty good. It's just not, I'm more interested in really the methods. Basically, they took this cyclobutadiene, which is this CH4H. And basically it has this it's a very interesting structure and very reactive and hard to model. It has this isomerization effect, so it kind of rapidly shifts between different given energetic sources. And it's been really difficult to determine how much energy this actually gives off. A lot of the other experimental methods are kind of widely varied, and even other simulation methods aren't as varied. This one had a pretty tight bound that was within the experimental method, which is actually pretty promising. And I think it is very interesting that all of these good results, and they had a bunch of other good results for a bunch of our molecules. So I did think that one of the strengths of this paper was that they seem to have good body results. They also said that basically they could control the determinants of the backflow and the other matrix that they were learning with the neural network. They were able to actually use that with a small number of determinants, which was pretty efficient. The one drawback I saw was that, again, you need to train for each molecule individually. But it did seem to provide this really interesting combination of both this real-world physics knowledge and also deep learning approaches. So thanks for joining for this quick review. Appreciate it. Have a good one. Make sure to smash and like and give me all a subscribe. Really appreciate it. Helps me out a lot. Thanks.